Epimers. All of these fancy little words that we have to understand in the world of carbohydrates. So, disaccharide, monosaccharide, aldoses, pentoses, trioses, tetroses, and now this word called epimer. Right? It's just to make us sound smart. It makes us sound like we know what we're talking about when we might not. But it's a fancy little word that I can kind of throw around that does mean something. So in this video, we're going to talk about this term epimer, how it relates to stereochemistry and configuration. And then we're going to look at a family of carbohydrates and really pick out what the epimers are and pick out the ones that you should know by heart. The structures that you should be able to draw blindfolded. So these are the structures that you need to marry and you need to take home in the bed in your mind and draw them over and over and over and over. And there's not very many of them. There's a couple. So I'm not asking you to do tons of memorization, but there's a couple out there that you should know. Alright, so let's first talk what a epimer is all about. Back in the previous videos, we talked about R and S, right? And R and S stems from the fact that we have a carbon here in the center called a chiral carbon, right? And this chiral carbon probably has on it 4 groups. It has to be chiral, and those groups are probably an aldehyde or a ketone, and a CH2OH group, and a hydrogen, and an OH group somewhere along the way. Right? So if we're given the choice, we prefer it to draw that way. Maybe the book will give me a structure in a different orientation. We talked about how to handle that in the previous video. And if I wanted to label this as a D or an L sugar, let's classify it here. Let's just take some time to classify the sugar. Okay, so number 1, it is a aldehyde group. So this is a aldo, and this is a 1, 2, and 3 carbon chain. So this is a triose. So aldo triose is what I have. And then this does match the template for the shortcut. Aldehyde at the top, CH2OH at the bottom, and the hydrogens and the OHs are left and right. The OH group, well, that group is to the left, so that means that this is the left-hand version of the sugar. So this is the levorotatory version. If I didn't want to use L, what other letter would I use? That's right, you would use the S form for sinister. So this is a L-aldo triose. Now this has 1 chiral center, right? So there is a version of this structure that's out there that will basically be the flipped version, right? C double bond OH and then a CH2OH here. And this OH and H can flip spots. So hydrogen could be on this side and OH could be on that side. Well, okay, what if I wanted to do the classification here? Well, as you would expect, nothing really major changes. This is still an aldehyde, so it's still an aldo. It's still a 3 carbon chain, so it's still a triose. And this time, however, the OH group is on the right-hand side, which means that this is the D version of the sugar. And if I didn't want to use D, I could also use the R. So D or R form of the aldo triose. Alright, so chiral center, you have 2 options. You could have a left version or a right version. This is what we've been talking about really for video after video after video. The problem, however, is that once you get out of 1 chiral center, we've kind of already discussed this thing, right? Once we get out of 1 chiral center and we go to 2 chiral centers, the story gets a little bit more complicated on us. So C double bond OH, and we still have CH2OH here. And let's just put 2 more carbons in the center, and let's put OHs here and hydrogens here. Alright, so that's one version of another sugar. This one, however, has two chiral carbons. And if it has two chiral carbons, known as asymmetric centers, then this thing has four stereoisomers. Okay, well, what does that mean? Well, we could put the OHs here, and that would be a sugar, right? Or we could have flipped this thing around. So we could, if we wanted, put both OHs on the left-hand side. And that would be deemed a different sugar, right? So here's a sugar, there's a sugar. Well, I chose to put my OH groups on the same side. I didn't have to, right? So I could have put maybe one on the left-hand side and one on the right-hand side. That would be a different sugar. And then finally, I could flip that orientation around a little bit. And the OH group that I chose to put on the left here, well, it could go on the right-hand side there. And the OH group that I chose to put on the right-hand side here could go on the left-hand side there. And that's a different sugar. So what you're going to see is complications that begin to happen. The more chiral centers that these sugars have, the more possibilities of sugars that you have to draw. And each one of these sugars are completely different. And some of these sugars go by different names. So stereoisomers, again, are very important. Now notice what we've done here. My aldehyde's at the top, my CH2OH group is at the bottom. If I wanted to label this as a D or an L sugar, I can quickly do them because they match the template, right? I look for the last OH group in the molecule, and that's going to be here. So this is on the right-hand side. That's a D sugar. This is on the left-hand side. That's an L sugar. This one is on the right-hand side. That's a D sugar. And this one is on the left-hand side. That's an L sugar. So I've quickly used our shortcut to determine if this sugar is the D form or the L form. If I added another carbon, the number of stereoisomers increase yet again. So the ones that have 3 asymmetric centers have 8 stereoisomers. The ones that have 4 stereo centers have 16 stereoisomers. So they begin to greatly multiply when that begins to happen. Alright, well, diastereomers, that's what these things are called. So diastereomers, let's make a new definition. Diastereomer. And this is a term that we used back in stereochemistry, it's not new, that are different in configuration at only one chiral carbon, are called epimers. So that's the term for epimer that you need to know. So what does that mean? Well, if I go back up to these structures, everything in the structure is the same, but the OH groups are flipped around on me, right? And because they're flipped around on me, they're different at 2 chiral carbons. They're different at this one and they're different at that one. They're different at this one and they're different at that one. So these two structures, the first two, they are not called epimers. They are different at more than 1 carbon. So not an epimer. That's called something different. That's a diastereomer, right? We get kind of the same structures and we take the mirror image, and because we've taken the mirror image, well, it's kind of a diastereomer definition, right? Okay, so what would be a diastereomer here? Well, I need to look for a compound that's only different at 1 carbon. So if I take a look at this first one and at number 3, notice everything's the same except for this second carbon in the chain. So this one and this one, these two things are called epimers. And that's because at this carbon, the OH and the H are in a different position. Everything else is staying the same. It's not moved. And that's the definition of an epimer. We get a structural difference at only one chiral carbon. And that, by definition, is called a epimer. What type of epimer? We can classify it a little bit more if we want, and we say that this is a C2 epimer. And the reason for that is because at my second carbon, that is where they're different. So this is my first carbon, this is my second carbon. So at carbon 2, they are flipped, and we call these a C2 epimer. Okay, well, what about number 1 and number 4? Well, it looks like number 1 and number 4 could be epimers as well, right? I see the aldehyde up here at the top, and I see the aldehyde down here, or the CH2OH group at the bottom. I see that at my second carbon, nothing's changed. My OH and the H's, they've stayed at their location. At the third carbon, though, at this point is where they flipped. My OH has flipped to the other side. So yes, number 1 and number 4 are epimers as well. And this epimer is called a C3 epimer because at the third carbon, that chiral carbon is the one that flipped on me. So this is the story with epimers, and that's how as easy as it should be to label if something is an epimer or not. You look at the two structures, you figure out what's different. You know, what got flipped. If only one of the carbons flipped around on you, then by definition that is called an epimer. My advice is to go back and review the term diastereomer and review the term enantiomer. Okay, so an enantiomer basically is like your left hand and your right hand. You take a mirror image of a molecule, and if those molecules do not overlap, then they are classified as enantiomers. Hence, R and S's. Those are enantiomers. Diastereomers are something a little different, and I'm not going to tell you what that definition is going to be. I want you to look up that definition, and I want you to review that definition on your own, because I want you to put a little bit of work in it, right? So go back and review diastereomer. So enantiomer, diastereomer, and now this term called epimer. So don't be surprised if you get these questions and it says, are the following epimers, yes or no? And if they are epimers, tell us what type of epimer it is. Is it a C2 epimer? Is it a C4 epimer? Is it a C6 epimer? So that's the term. That is how we classify sugars as epimers or not. And in the next video, we are going to begin to look at a flow chart of carbohydrates now that are epimers of each other and start picking out and labeling what these carbohydrates actually are. So good luck. Keep reading the text. Take a look at the flow chart that's coming up, because you might need to take a look at it more than a couple of minutes to understand the type of information that they're giving to you.